Welcome to this video. My name is Mark Scythian. The date today is July 6, 2024. This video is going to focus on the practical use of the derivative in calculus. So here's an example. A car accelerates from rest and travels 1,450 feet in 15.5 seconds. What is the car's velocity at 5.0 seconds and 12.0 seconds? What is the car's acceleration at 7.0 seconds and 15.0 seconds? Is the acceleration constant over the function of time? So the first step is to define what velocity is. It is a speed in a certain direction, and that speed is the distance displaced over a period of time, or d, divided by t. Then defining acceleration, delta v, or the change in velocity, so the final velocity minus the initial velocity, delta v divided into time. So essentially we're dividing the velocity change, or the change in distance, divided into time, then dividing it into time once again. So then acceleration is also equal to distance divided into time squared. So if we took 1,450 feet distance and divided it into the quantity of 15.5 seconds squared, we calculate 6.04 feet per second squared acceleration as the car accelerates from rest and travels 1,450 feet in 15.5 seconds. This is equal to an acceleration of 6.04 feet per second squared. So the acceleration and the velocity are different types of rates of change, or slopes. These are also known as derivatives. So velocity is a derivative. The slope, or rate of change, distance divided by time. Acceleration is another slope, distance divided into time squared. So if we plotted these two on a graph, the distance would be on the y-axis, the vertical axis, and the time would be on the horizontal, or x-axis. So time goes in, distance comes out. That is the function. So that is the y divided by x, or the slope, or the derivative. So the second derivative is the acceleration, or the first derivative, velocity, then divided by time once again, to become the second derivative. Velocity is the first derivative. So the integral, or the reversal of the derivative, can be applied to the acceleration, or the second derivative, to then solve for the first derivative, or the velocity. So we can use a check test method to simply convert the constant 6.04 as the acceleration into the velocity, or the first derivative. So this would be a definite integral with the upper limit 15.5 seconds and the lower limit 0 seconds. So 6.04 as a constant, its derivative x, or dx, then converts the constant into a first derivative or velocity. So the constant acceleration, then going to a function of the first derivative. So if we use the rules for integration, we raise the value of its exponent taken from a constant into a first derivative rate of change. So this then simply reverses what the derivative of 6.04x would be, a constant of 6.04. So the reversal, or its integral, is 6.04x, then to the first power, then divided by 1. So 6.04x describes the velocity or the first derivative. So that would be over the time limits of 0 to 15.5 seconds, or x representing time. So x is equal to or greater than 0 and equal to or less than 15.5 seconds. So that's the time period or the time limit on the x-axis, or the time axis. So 6.04 with 5 seconds substituting for x becomes 6.04 times 5. So that is 30.2 feet per second velocity at 5 seconds. At 12 seconds, then 72.5 feet per second. So if we solve for the velocity at 7 seconds, 42.3 feet per second. Now if we solve for the acceleration, or the change of velocity, so the final velocity at 7 seconds is 42.3 feet per second minus the rest velocity of 0, delta v, then divided into 7 seconds for the acceleration. We calculate 6.04 feet per second squared at 7 seconds. Then the velocity at 15 seconds, 90.6 feet per second. And then the change of velocity, 90.6 feet per second at 15 seconds minus the rest velocity of 0, then divided into 15 seconds. We also compute 6.04 feet per second squared acceleration at 15 seconds. So the acceleration is the acceleration constant over the function of time? Yes, it is. Acceleration is constant over the function of time. So we're already dealing with a constant second derivative acceleration, then converted into its velocity. However, to prove that the acceleration remained constant, we can also solve for the velocity first and then the acceleration second at 7 and 15 seconds respectively. So the final answers to the problem are 30.2 feet per second at 5 seconds, 72.5 feet per second at 12 seconds, and a constant acceleration of 6.04 feet per second squared at both 7 and 15 seconds. And yes, the acceleration is constant over the function of time. Thank you for watching this video and have a great day.